Boeing spent $2 million on wind tunnel testing for the 787 Dreamliner, over 12,000 tunnel hours, and CFD had already predicted 80% of those results before a single model entered the facility. So why spend the money? Because the 20% CFD missed included critical buffet onset and control surface hinge moments. Today we're answering the biggest question in simulation engineering. We'll cover where CFD dominates, where tunnels are irreplaceable, and the hybrid approach every serious team uses. When you run a CFD simulation, you get data everywhere: velocity, pressure, temperature at every single cell. A wind tunnel gives you data only where you place instruments: 50 pressure taps versus 50 million data points. Then there's iteration speed. Changing a geometry in CFD means modifying a CAD file. In a wind tunnel, it means fabricating a new model at $50 to $500,000. Weeks of lead time. CFD lets you sweep 50 design variants in the time it takes to schedule one tunnel entry. And cost. Tunnel time is $10 to $50,000 per hour. A comparable CFD run on cloud compute costs a few hundred. Later, I'll show you why these advantages don't tell the whole story. Think about what full flow field access means in practice. Designing an automotive air intake, you can visualize exactly where the separation bubble forms, track secondary vortices eating your pressure recovery, and see velocity profiles at every cross section. No gap in understanding between measurement stations. This is powerful for internal flows like HVAC ducts, turbo machinery passages, and heat exchangers, where physical instrumentation is intrusive or impossible. And you interrogate data after the fact. Realize you need wall shear stress on a surface you didn't plan for. In CFD, it's already there. In a tunnel, that's another test campaign. Now, here's where it gets complicated. Every turbulence CFD simulation relies on a turbulence model, and every turbulence model is wrong. The question is how wrong. RANS models like K omega SST solve averaged equations. They don't capture individual eddies. For attached flows and mild pressure gradients, drag predictions land within 2 to 5%. But hit massive separation, a stalled wing, the wake behind the bluff body, and RANs can be off by 20 to 40%. The physics of separated flow is inherently unsteady. Averaging it away isn't a software bug, it's a fundamental limitation. In a moment, we'll see why even the most expensive approaches can't fully solve this. Why not resolve turbulence directly? DNS, direct numerical simulation, resolves every eddy down to the Kolmogorov scale. No modeling. But for an aircraft at Reynolds number 100 million, you'd need 10 to the power 20 cells. The world's computing power can't run that. Large eddy simulation is the middle ground. LS resolves large energy carrying eddies and models only the small ones. Far more accurate for separated flows, but less costs 100 to 1000 times more than RANs. An 8-hour RANs job becomes 8,000 hours in less, and while resolved less at high Reynolds number scales as re to the 2.4. Every order of magnitude multiplies cost by 250. Two more problems that keep wind tunnels relevant. First, laminar turbulent transition. Predicting where flow transitions depends on surface roughness, free stream turbulence, pressure gradients, and instability mechanisms that interact in ways we don't fully understand. Wind tunnels capture it naturally. CFD needs explicit transition models like gamma ret theta, which are empirical correlations, not first principles. Getting transition wrong by a few percent of chord swings drag by 10 to 15%. Second, wind tunnels capture physics you didn't model: aeroelastic flutter, acoustic resonances, condensation shocks. CFD only predicts what you program in. A wind tunnel captures everything, including phenomena nobody anticipated. For novel configurations like blended wing bodies, where we lack historical databases, this matters enormously. Even if CFD were perfect, there's a practical barrier. The FAA and EASA don't accept CFD as sole evidence for critical aerodynamic performance. Aircraft certification requires tunnel data and flight test data. Period. In wind engineering, Cladding pressures for structural design must come from boundary layer wind tunnels per ASC 49. In automotive, published drag coefficients are tunnel measurements, not CFD. The regulatory framework lags behind technology, but that lag exists for good reason. CFD carries modeling uncertainty that's genuinely difficult to quantify. So, how do world class teams actually work? A carefully orchestrated hybrid approach. In aerospace, Boeing and Airbus use CFD for 80% of design exploration. Hundreds of variants evaluated before a single tunnel model is built. Then targeted campaigns validate the final design and generate certification data. In Formula One, the FIA mandates a 60-40 CFD to tunnel split. Teams strategically allocate each. CFD handles parametric sweeps. The tunnel validates aero maps and captures effects RANs misses like tire wake interaction. In automotive, tunnel hours dropped 50 to 70% over the past decade, but every major manufacturer still requires final validation. When you're claiming drag coefficient to 3 decimal places, you need that tunnel number. The gap is narrowing fast. GPU accelerated solvers deliver 10 to 50 times the speed up. Week long simulations complete overnight. Machine learning surrogates predict flow fields in seconds for real time design exploration. Wall modeled LES is becoming affordable at industrial scale. Full vehicle aero in LES, a research exercise 5 years ago, is now routine at major manufacturers. NASA's CFD Vision 2030 identified three barriers: turbulence modeling, mesh automation, and uncertainty quantification. Those barriers are falling. But falling doesn't mean fallen. Here's the practical takeaway: a traffic light system. Green, trust CFD. Attach flows, pipe flow, heat exchangers, low angle of attack external aero. RANS gets you within 2 to 5%. Amber. CFD gives trends but needs validation. Moderate separation. Complex 3D flows, transitional regimes. Anything where turbulence model choice significantly changes the answer. Red. Don't trust CFD alone. Massive separation, flutter boundaries, novel configurations with no validation history, certification data, wind tunnel required. The skill of a good CFD engineer isn't running simulations. It's knowing which category your problem falls into before you start. Can CFD replace wind tunnel testing? Not yet. Maybe not ever completely. But that's the wrong question. The right question is how we use both tools to make better decisions faster and cheaper. CFD has cut development timelines by years and cost by millions. Wind tunnels have evolved too, more sophisticated and targeted than ever. The best engineers don't pick sides. They understand strengths, limitations, and deploy strategically. Master your fundamentals. Validate relentlessly. And never confuse a beautiful contour plot with a validated result.